All right, welcome back everybody to the Additive Snack podcast. I'm your host, Fabian Alefeld, and today I'm super pumped, super excited to welcome back Thomas Pomorski from Ursa Major. Since Thomas was last on the show, it's almost been a year now. Of course, a lot has happened, not only in additive manufacturing, that's happened at Ursa. A lot of news and interesting innovation coming out from that team, especially around Thomas, from liquid rocket engines to hypersonics to solid rocket motors, new facility groundbreakings, and more. So we'll talk about what's new at Ursa. But at the same time, of course, in the last year, a lot has happened in the space of manufacturing, of additive, and in the space of AI. So we'll also talk about how Ursa is applying artificial intelligence in their programs, how they see AI, but also other innovative technologies implementing and affecting manufacturing from their perspective, and overall how that is going to change the way we build innovative applications. So therefore, as I said, super excited to have you back, Thomas. Welcome to Additive Snack.
Hey, Fabian, thanks for the introduction. I'm really excited to be here. I think you're doing a great thing for the industry, and I'm happy to be a part of it.
Yeah, so do you. You continuously innovate, but you also talk about it. And therefore, I really view you as one of those leaders in the industry that helps us to grow the space, to share innovative insights, and therefore really advance the industry forward. And before we dive into some of the really cool stuff that you're doing at Ursa, let's maybe take a few steps back. Like I mentioned, it's been a year, especially in our industry. A year is a lot. So yeah, what has happened at Ursa in the last 12 months?
Yeah, absolutely. So we've had a lot of exciting things happen over the last year. Ursa right now is focused on 3 products. One is Hypersonics. The second is solid rocket motors, and the third is in space propulsion. We think these 3 areas are really key unlockers for the defense industrial base in the U.S. And we've had really exciting things happen on all fronts. So for Hypersonics, we have successfully flown over 9 hypersonic missions with a reusable 3D printed Hadley engine. So it sounds, pretty crazy to say, but yeah, we've flown our Hadley engine, which is an oxygen-rich stage combustion engine, over 9 times with our partner Shadow Launch. Some of those missions have been with an engine that's previously flown hypersonically. So we've flown on a mission, gotten the engine back, did this, inspections, flight overhaul, and then flown it again. And these engines are, roughly 80% 3D printed by mass on actually EOS hardware. So that's one thing. That's our cryogenic liquid oxygen kerosene engine. We have a storable version that we call Draper, and Draper has actually had 2 successful test flights with a program with AFRL in the past few months. So we built a full vehicle ourselves, and we integrated the Draper engine onto that vehicle. Again, that engine's primarily 3D printed, and both of those test flights were successful. On the solid rocket motor side, we've also been working on our LINX manufacturing process. We've talked about it a few times, but we actually have a full mix, cast, and cure facility at our headquarters in Berthoud, Colorado, where we're doing the propellant formulations, we're mixing it, we're doing all the manufacturing for the case, we're pouring the propellant, and we're test firing them all. And we heavily use additive both on the tooling side, but as well in the actual cases, to enable flexibility. So one of the biggest problems right now in the U.S. is that we're depleting a lot of the munitions. So we need to have a new manufacturing process around solids that enables scaling different types of products that don't require that fixed tooling, right? And that's what additive is so great. So we're building this unit cell approach around our solids that we can build any size, any type of motor And then when we qualify the unit cell, then we can scale that to multiple different sizes, different platforms, things like that. So we've had multiple test flights successful of solid rocket motors as well. So yeah, it's been an exciting year on the product side. And then on the additive side, we've had an equally exciting year. So we've gotten multiple EOS M450 machines, which we had announced a few months ago with you guys. We're running those machines. They are amazing. They have 4 end lights in them with upgraded gas flow and optics and things like that. And they can really crank out some material. And then on the slicer side, we've been really working with Dendrite and with folks from EOS to develop what we think is one of the most advanced slicing pipelines in the entire industry. And we've been printing hardware with that for the last few months, and that hardware is being hot fire tested and actually being put in applications as we speak. So we're continuing to refine that and build it out. We've learned a lot, but yeah, it's been a lot of exciting stuff over the last year.
It's awesome. Yeah, you guys are definitely not slowing down. You guys are you're going hypersonic yourself.
That's right.
Yeah. Let's maybe, before we go deeper into additive, because I want to ask you a lot about those especially those software innovations that you guys are working on.
Yeah.
Let's maybe double click on hypersonics versus solid rocket motors. What are some of the key challenges of hypersonic propulsion? Right, it's one of the hottest bakes in the defense sector at the moment. What are some of the challenges of that application, and how is additive helping to solve those?
Yeah, absolutely. So the biggest challenge to hypersonics is building affordable production system. So like, it's not that hard if you have hundreds of millions of dollars to build a hypersonic system. Like, we've been doing it for years as a country, but those are basically test vehicles or very bespoke applications or extremely expensive. So the real holy grail is, can you build an affordable, manufacturable hypersonic vehicle? And there's a couple different avenues that you can go down. So there's some air breathing systems that are using high-end production, like a ramjet or a scramjet, some other exotic propulsion systems, rotation detonation engines, things like that. They're air breathing. There's some potential solid applications. And what Ursa thinks is a unique application is we have a liquid rocket engine version, which is around our storable Draper engine. And so what's nice about this engine is that it enables a lot more flexibility in the profile of the flight, in that doesn't need oxygen. So because it carries the oxidizer, which in this case is hydrogen peroxide, with it. That also means that you don't need a really sophisticated ignition system, because as I'm sure a lot of people know, a lot of the more exotic propulsion systems have to already be traveling really, really fast to get started, like a scramjet or a ramjet. So you have to now build a vehicle. You have to be able to test the ignition in supersonic or even potentially hypersonic regimes using one of those systems. So now you can imagine how expensive that testing is, how difficult building all of those systems are. So what we're trying to do is say, hey, we have this liquid rocket engine. We can test it in any regime. We've already flown hypersonically. We know how to use an engine there. You can test it on the ground. And we know how to build additive hardware affordably. So we really think we have a novel approach to solve what I think is the biggest challenge, in that providing a low cost, in the low $1 million range, full vehicle that can enable hypersonic applications.
Interesting. And you're therefore also, increasing the ease of deployment, right? Because you don't have to start in flight, and therefore, do you understand that?
Exactly. Yeah. So we can have a booster attached to increase the range, but there's no really requirements on starting it. So you don't have to air launch it, that you can. So you have, like you said, you have a lot more flexibility, and it'll lower the cost to qualification and production as well, because again, we don't have to validate the operation in these super challenging regimes. Like, I mean, to test in a wind tunnel that's supersonic is very expensive, right? So you have to make back all of your R&D cost on these. So, there's a lot of competing ideas, a lot of competing systems, but for any of them, the end use vehicle, full vehicle, has to be low cost. And what that exactly means, like I said, probably on the order of like $1 million a unit, but it can't be 20, 30, $50 million. And right now, a lot of the bespoke applications that we have in the US are, test vehicles, target vehicles, and those are talking tens of millions of dollars per flight.
Interesting. So when it then comes to your engines, really, it's interesting because, for the longest time, if you think of additive, people always think of an expensive manufacturing technology, right? And now we're actually at a point where additive allows you to be more cost competitive than probably conventionally manufactured engines, which is also, to me, again, a huge testament to the technology. And now, if you talk about solids rockets motors, I mean, here you have an even bigger cost pressure, of course, right? Because now you're competing with cast material. What does that whole production chain look like, and what exact role does additive play? You mentioned a little bit about using additive in tooling. Where does additive add value to the solid rocket motor production?
Yeah, so solid rocket motors have an extremely competitive cost profile, but the challenge around solids right now is that they're all built on fixed manufacturing lines. So a manufacturing line can make, let's say, 400 13-inch motors a year. Well, if you want 1,400, or if you want 401 motors, you have to build a whole new production line. So that production line is going to cost you a few $100 million. So, yeah, they'll be cheap once you get to that rate, but you have to invest that capital. You have to amortize it over time, and you have to make that commitment up front. Whereas maybe in 2 or 3 years after the production line is built, maybe we want a different product, or maybe the industry has innovated and that product's no longer relevant. A good example as to this is the use of small, cheap drones. So maybe things pivot where we don't want these like larger, more expensive solid rocket motors. Maybe we want a lot more smaller ones. Well, now you just built the production line, which took you 3 or 4 years to now produce, the larger ones. So where Ursa's really focusing on with additive, right? Because one machine can build, let's say we're building a section of a solid rocket motor. We can build a 4-inch, we can build a 10-inch, we can build a 14-inch, all on the same machine. So if you go to what we're calling a unit cell approach, where you develop all of your tooling such that it can handle multiple different sizes, then you can set up your factory for one size, and then you can basically just change the digital manufacturing requirements and the product design, and then you could build the different size motor. So that's where we think a lot of innovation can happen in the solid space, and that's what we're focused on addressing. And on the additive side, we do it both for tooling as well as actual in cases as certain materials. So there's certain features in solid rocket motors that are really complex, that are typically, they're either forged material or cast material, and the lead times on those are extremely long. So again, if you're setting up production line, you do a large order, the material will be here in like a year. Like the lead times for the more exotic materials are about a year. There's some like high strength steels and things like that, more aging steel, RMET 100 is another big one. So the other thing that we can do is we can go in and get these materials and we can build these things super rapidly, and then also apply Ursa's philosophy of design, print, test, iterate. So we're kind of addressing multiple different challenges all at the same time with our design and our manufacturing process.
Interesting. Yeah, so you really have two sides of the coin. On your Draper and Hadley, of course, additive is also really leveraging the design capabilities of the tool. Whereas in your LINX production, it seems really mainly a supply chain case. I'm guessing that there's not any unique geometries in your engines that leverage additive, or are you still including some of those potentials there?
Yeah. Oh, there still are challenging geometries. Now, I mean, we want these to all be drop-in replacements for what's out there. So we can't do anything crazy. We have designed and hot fire tested crazy designs that utilize additive, double wall things with insulation and like lattice structures and things like that. And we've tested them and they work. The industry is not ready for that yet. Right now, the industry wants is drop-in replacements for the platforms that they already have. And then I think in, 5 years down the road, then we'll be ready for more advanced solutions. But, our process is agnostic. So yeah, the parts we're printing they're still fairly challenging, but a lot of them could be made conventionally. However, again, you have to build in a factory, you have to build a production line, you have to pick what you're going to do. And that does not allow flexibility. And as the world keeps evolving, just think about how much we've done in the past year. All of the additive manufacturing is evolving so fast. So, to me, I think there's a lot of value in building that flexibility in from the ground up. Again, cost, if you factor in the entire cost, is fairly competitive. The unit cost is going to be a little bit higher, but you don't have to have the full production line factory cost, because you can also build each unit cell, organically as you need the production, right? So when you're investing CapEx in a facility, you have to build the whole facility before you can get a single motor off the line, right? So in here, we can build one unit cell, we can get low rate production, we can do qualification testing, and then we can just boom, 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 duplicate the unit cells as we need to scale. So it also helps spread out the capital as well, which is good for startups and VC funding.
Yeah. No, it's very exciting moment in time, right? Where we see additive contributing to those types of programs that I think even 3 to 4 years ago, we would have not thought that they would be even close to being cost competitive. But now the technology is mature enough, it's reproducible enough, it's scalable enough where you see applications like yours. You even see, right, consumer good applications where additive is cost competitive to conventional technology. So it's a very exciting time, just from a hardware readiness perspective. And then, as we discussed earlier, right now we're starting to see slowly AI creeping into our fields, right? I think if we compare it to other industries, we're still at the very, very early beginnings in additive. And if you watch, for example, Dwan Scott, he tests every tool that's out there on a prompted design basis. Most of them fail, but some are actually impressively good, right? Because he always uses the same geometry of a monitor mount that should be somewhat simple, but most tools fail. Then Autodesk announced a prompt to parameter optimization tool. So there's a lot happening. And now even Claude came into this space with a collaboration with Fusion. There's probably even more that I haven't even seen. So let's maybe start there. So where do you today see value of artificial intelligence in the manufacturing/additive manufacturing sector?
Yeah, so I use AI every day in additive development. And so right now it's already useful. So where I use it is I mostly use Claude Code CLI tools.
Okay.
And I'm working on two main things. So one is, we talked about Placer development. You can use it to develop algorithms and design experiments and new functions very rapidly that we can go and test out. So I might say, hey, I read a paper about this new scan strategy. Maybe it's a spiral scan, or maybe it's island scanning, or whatever else. I can go plug that paper into Claude Code. I can give it our slicer repo and say, hey, go and build this function in our repo, and then I'll go test it out. So they'll go and build it, we'll verify that it works. I'll slice it, the new algorithm, and then I can go and test the algorithm on our printer. And I can do this rapidly and iterate. And then once we find something that works really well, then, we have a software team as well, and they can go and they typically rebuild things because, the tools right now, there's anyone that uses them knows, they still aren't mature enough to go into a critical environment that we have, and you can trust everything that they do. So, we've been rebuilding a lot of those things, but that fast iteration, which is really what we're after. I'm really focused on acceleration. How do we do more? How do we go faster? And this has really enabled us to screen for new ideas, new parameter strategies, new scan strategies, in a really, really quick way, so that we know things we need to focus on. And then on the back end, I think, so that's on the front end of the additive workflow. On the back end, the other thing we've been using it for is to help a lot on the data processing, data management side on the additive. So we can go through this later, but I built a full data fusion workflow, all with AI, where I can pull all the data off of our EOS machines, put them in a database. I can view the data. I also played around with defect detection, and then powder bed images, live camera feeds, all that stuff I built from the ground up with AI. And then what's nice about that is, again, I can test all this functionality out, see what we want, see what's useful. I can show engineers it, say, hey, what's useful? What do you like about this? And then we can go and spec out the software that we actually want to build. And it makes it a lot easier to deploy this to the software team, where we already have a full framework built out. Here's what we need. Here are the requirements. And then they go and polish it off in a very robust, production ready way. So those are two cool applications.
Wow. So you really, when you're using AI to prototype in different aspects, right? To prototype really new parameter strategies, but also to prototype software that then your software team actually writes from the ground up. Probably still with AI help from Cloud Code or Codex or whatever, but in a more mature, non-vibe codey way, I can imagine.
Exactly. Yeah. I mean, when I'm doing it, I have a day job which isn't coding all the time. So I'm kind of doing this on the side. So I'm doing large projects with AI, which then adds in all those type of vibe coded defects that we love to laugh about on the internet. So it's great for development for the way I'm using it, but then the software engineering team, they can use it for very, very small things and give it very directed instructions, and that works really, really well to more rapidly develop more mature software. But and we'll see. I have a good example that we can go through, and hopefully it'll work out. But I'm giving it very broad instructions. I'll give it a lot of details about what I'm after, but then I let it go off and do its thing. And again, great for prototyping development, and it just increases that development speed, which is what I'm really after.
Yeah. I mean, because it's not been that long ago, you remember pre-Claude and now post-Claude. How much more efficient would you say these tools make you? Like, would you say, that a lot of the development work you're doing, you wouldn't even be doing because it would be much effort? And would you say you have twice the outputs, twice the what was that X look like on your end?
Yeah, I mean, it's hard to even put a number on it, but I would easily say 2x or 3x the amount of like DOE and experiment output because of this capability. Because I don't like, this is all stuff I can do myself. But I'm super busy. You know, we're building a team, we're building machines, we're qualifying hardware, we're getting feedback from hypersonic flight, we're doing design for additive work with engineers, we're developing new workflows. Like that's my day job. And then, you know, on the side, I have Claude running, you know, and Claude agents running. And then I'm like, all right, let's build this. Let's do this DOE. Like, here's this paper. Like, what do you think about this? And so like I can use, let's say 5% of my time and do the work that a full engineer could do, on the side of my jobs.
Yeah.
Yeah, it's really amazing what it enables. And this is just the infancy. You know, we're still using a fairly outdated version of Claude because it has to be compatible with AWS GovCloud, which is like 3 or 4 versions behind. So we're using like, you know, 4.5 and now they're, you know, all the way up to Mythos preview for some people. So I think there's a lot more potential. And as these things continue to evolve, like, we're going to be able to use this more and more and more. So what I say now is, like, people need to start figuring out how this fits in the workflow. And even if it's not directly useful on the production side, like, I really confident it's useful on the development side. And people need to understand where it's at and like the level of maturity it's at. Like right now, because like I said, I'm using it every day. It's already useful on hopefully we can do a demo and we'll see it work in real time, but it's only going to get better. This is still like the infancy of the capability, I think.
The worst it's ever going to be. Yeah,
exactly.
If you could show, that'd be awesome. Let's look into some of your workflows. And while you do that, so how many people on your team have the same approach? Right. So I guess my question is, if you're a 5-person team, everybody does what you're doing. You're now acting like a 15 to 20-person team, right? Same output as a 20-person team.
Exactly. Yeah, we have a very small team. There's just 4 of us on the development side.
Okay.
And we're outputting, I mean, like, we're a team of at least 10 or more with the type of workflows that we're able to develop. And it's actually even more because of, you know, the experience level that myself and some of the folks on my team have, right? Like the AI can almost be a multiplying factor if you already have the knowledge. Because if you tell it exactly what you want, it's really, really good at going and do those things. So like if you're an entry-level engineer and you haven't had that much experience in there, you're not going to get as much benefit out of it because you don't know all of the nuance around the type of factors that could be involved in the thermal profile, the thermal history of a part, like all those things. But if you can tell Claude, hey, these are the things I'm interested in, this is why I'm doing it, like, what are all the things that we should change? And then to come back with all these ideas and say, oh, like, this is the thing you should go off and do. And so it's like, as you get more experience in the additive, and then you can go and apply these technologies, it's like, it's almost like an exponential function of productivity where like you could have an army of, you know, less experienced engineers, and one person or a few people with these tools can do, you know, more work than an army of people.
Yeah. You're 3x, in 6 months, you're 6x, right? In 12 months.
Exactly.
Claude is screening papers for you, identifies which ones are worth prototyping, and will say, yo, Tom, I got 3 new strategies. Which one you want to print?
Exactly.
Very interesting.
So it's important to build those workflows now.
Yeah.
So this is going to be a really cool actual snapshot into how our slicer operates. So this is a VS Code environment, and we're using Claude Code CLI integrated with that. I've already pre-written some of the prompts, but we are going to run this in real time so you can see one of the actual workflows that I might do. So I'm prompting. I opened up a new Claude session and I'm prompting it, telling it it's an expert software developer for laser powered web fusion machines working on our slicer repo. Read through what we call the Polaris slicer and the build setup template and explain to me how it works. So this is good for a brand new instance of Claude to come in and understand the coding platform that it's working on and get everything it needs into context. And you can do this and create what's called markdown files to actually give Claude more or less notes on what it's doing and what it's read. So it's going to go through and read through the code, and it's going to tell me, hey, here's how the slicer works. It loads in geometry, has different parameters such as layer thickness, parametric angles, downskins, upskins, hatch parameters, contours, and then the configuration is driven through what we call TOML file, which has all of the input parameters. And then engineers can change laser parameters using these setup files without actually going in and editing the code. So what we're going to do now is I'm going to tell it the folder that I'm working in. So we're working in the EOS AI podcast demo. I'm telling Claude, hey, go take a look at this. Look at the generic setup file I have in there. Understand how it works with Polaris architecture. And then think about how we can use these functions in Polaris to make a part name specific segmentation or hatch group strategy. So the way that our code is worked up is we can name the parts certain things like sample 1, sample 2, sample 3, or any name that we want. And then we can give each part completely different parameter strategies automatically using these segmentation configs. So now I'm telling it, hey, here's the parts I've already put in this folder. Here's the generic segmentation, and we just have defaults in there for now. And it's gonna come in and learn all about that.
You're setting up.
Do you have any questions?
So you're automatically setting up a DOE in this case with unique parameter strategies for each test specimen without having to do any manual parameter application to the individual parts, but Claude does it all for you.
That's exactly what's going to happen. Yep.
Okay.
So sometimes it gets it. Here's one of the things that we had to try. Sometimes it knows the parts that are already in there. It didn't get it this time. So I'm going to tell it, hey, there's already 2 parts in this directory that we can use. What are their names? And then I remind it that the directory is there. And then it's going to hopefully come back and say, here's the 2 parts in there. Now we can go in and we can change the parameters. Yep. So here it is. So we have RDAM rec 126, number 1 and number 2. And so we can go in and have a build strategy for that. We can have different contours for that based on what we want to add. All right. So what we're going to do in this demo is we're going to try a different hatch pattern strategy. So a lot of people might use chess or might use stripes. We call it checkers. We're basically tiling core in the part, and we're doing this against gas flow. So we have an algorithm set up where we define the machine coordinates and then we scan into the gas flow, and that's how our standard checkers works. So it's pulling that out from the file right now. I say, hey, here's type checkers. We have 10 millimeter by 10 millimeter with 0.12 millimeter overlap. And it's going to show you the difference on an M400 platform, how it works, and why it matters, thermal management, scanning into the, and usually it gets excited and wants to do something. So I tell it, don't do anything yet. But now what I'm going to do is ask it to create a new scan strategy. So I'm going to say, let's keep the default checkers on part number 1, but I'd like you to apply a new strategy to the second part. So the new strategy should sort tiles from the center of a part, from the outside in. So if you have a certain thermal profile, or you have certain types of features that you might want to do on the part, we can now, instead of sorting to the machine coordinate frame, we can sort to each individual part that's on the frame. So it's going to come in here, and it always likes to jump around here. So I tell it, hey, here's what I want you to do. Here's where to go look in the code. I would like you to plan this task out. Here's what I would do: create a new hatch pattern function in the slicer, sort the tiles from the outside of the part, edit the segmentation file with this new feature, and apply the hatch pattern to part 2 using the TOML file. So it's going to come in here, and sometimes it gives me options. Sometimes it tells me everything I need to do. So this looks hopefully good. Implement a full solution, and I will test it. And so now it's going to go off, and it's going to edit the code. It's going to edit the setup file with the part names that are already in the folder. And we're going to give this a few minutes to do, and then we can check back on it here in a minute or two, when hopefully it is done.
So then, so how do you work then as a team? If one of you guys develops a workflow like that, do you have a shared prompt library that you guys share within the team for different workflows, or how is that then disseminated across the team, so that you guys don't reinvent the wheel, and you also improve and build upon each other's AI work here?
Yeah, so we have multiple GitHub repos that we use. So we have obviously GitHub repo for our slicer. We have GitHub repos for different setup scripts and things like that. And then we have internal wiki that we run. So it's similar to Wikipedia, but we have it internally for less official, more like helpful things. So we put a lot of helpful things around novel workflows that we create, and things that can help. We like to think about it as hey, you have a new engineer, or you have someone that wants to learn this. How do they do that? So we try to set it up as an educational resource. But I mean, we all sit next to each other. It's one of the benefits that we all try to be in the office, because we're also building stuff, and we like to see our hardware and things like that. So we also just talk about it a lot and play around with things. But I really like the wiki resource. It is pretty easy to host yourself, and with the AI tools being able to help you as well edit that. But it's easy enough that most people could do it on their own. That's a really good resource, because then it's easy to update too as things change. Because even I would say 6 months ago, a year ago, it wouldn't be able to do what we're going to do here today.
Yeah, a lot is changing. I think it's still thinking. So let me ask you this then: how far away are we from a production deployment, right? Because now we're talking more, like we said, DOEs, prototyping, development work. When do you start to see value of AI in production environments? And that could be a true AI developed process parameter that you qualify. That means qualification work itself of a new program and accelerated work. That might mean process develop parameters based on required material or part properties, right? How far away are we from a future like that? At least where it's maybe in a guided environment, just like you're getting guided when you're coding today.
I think we're still a fairly long way from that. I think the challenge with doing AI on let's say you're defining your thermal. All right, I have a good example. So there's a recent paper that came out. I don't remember the name off the top of my head, but basically they used a simple thermal FBA models to train a neural net model
Surrogate model.
to basically vibe simulate a part, right? So, and it reduced computation by like, 5 orders of magnitude or something. The problem with that is now, how do you validate that there's not some edge case? How do you because you don't actually know what it's doing, right? I mean, you have some idea on what it's doing and the patterns and things like that, but you don't have a good insight, especially into the edge cases. So I think that we need functions to better qualify how the code is functioning so that we can perform a lot more like unit testing on certain aspects of the code versus just testing the output of the code. And I don't, and I think that's going to take a long time before we actually have like ways to go in and validate those sorts of things. So I don't know if you had to put a number on it, I would say 2 years, but like it's going to be able to do those things probably in the next 6 months. But it's going to be really, really hard to validate. The validation's way longer than it is to build all of these tools.
Then that really also still means a huge benefit, right? Because even if it's even if it's just a FEA surrogate model, but it can tell me instantly while I'm designing a new part that I'll have distortion here and issues there, right? I have immediate feedback. I can design something very close to perfect. Now I run my final FEA to confirm this, and I still have saved a lot of time, and I probably still have a better product that will print pretty much immediately without issues. Because I've gotten continuous feedback throughout my engineering process.
Yep. So let's jump back in here. So it just finished what was built. So the new feature sorts tiles based on each component's centroid rather than the global reference point, enabling part-specific thermal management strategies. So it came in, it added a new function that identifies a part coordinate system in our hatch tile sorting function, and then it sorts to a different sort point. So now there's 2 parts in that folder. One uses a standard checkers strategy. The other uses the checkers outside in sorting. It automatically edited the setup file, added the parts. I didn't have to do anything. I've only done exactly what I showed you guys. And now I ran the part. So it imported the 2 parts. There's 2 20-degree cones.
Oh, cool.
Printed, they're labeled here. And one thing I didn't show you that's also built in our workflow, it automatically generated the support.
Wow.
If you color the surface emerald or pink, purple color, it automatically builds supports up to that surface. So all I did was click run on the setup sheet. It automatically imported these parts, applied this new strategy that Claude code came up with, and we told it to run, built the supports, and now it's slicing for our EOS M400. And hopefully the output looks good. It's going to take about 10 minutes. We'll double check the output, and then we'll try to actually start it and run it on the machine so we can see the algorithm we developed just in the span of a portion of this podcast.
That's awesome. And that's probably, especially if you have a full plate, right? That's a days of engineer work.
Oh yeah, and I could have asked it to try anything. I mean, I could have developed an equation for thermal management around the 20-degree angle, and I could have put, normally I run a lot more parts, but I just have a couple on here, so this is simplified. But I could have a whole plate of parts. Every part's named differently. I could just have a giant Excel sheet that's not formatted or organized or anything, and just things are kind of labeled. I could tell Claude, hey, make a setup file with this sheet. It'll make that file. It'll give each part different parameters, and then I can just go and run it. And it takes me 10 minutes to do the most complicated DOE you can think of.
Crazy. Do you see a future where you go through this process, now you print it, while you print it, Claude has access to the OT thermal profile, detects that some parameters do create overheating, adjusts them on the fly, right? So that after layer 1000, you've actually gone through, as you go through Z, you've gone through even more iterations of your parameters, and you end up with like one winner.
Yeah, absolutely. I mean, and to build on like where this is going next, and it's absolutely the ability for Claude to now go out of the coding environment and start interacting with other types of data streams. So like, one of the new tools that's coming out or is out already is the ability for Claude to control different functions on your computer, to control, different programs, and to work in different contexts. So, yeah, being able to go in, like the ultimate would be, hey, go find this program, understand how it works, pull the data, figure out how to interact with the data, and then now compare it back to the slice that we just created. So like, we could do all that now, but it would require a ton of my time to go in and say, okay, here's where the data is, go here, pull the data. Like I'd have to do very manually. The real big unlock, like the next like step change, is when I can just tell it what I want. Hey, let's go compare this to OT. Here's the machine that has it on it. We already ran the build. Go figure out how to do it. And then once we do that, I mean, it's going to be another, 10x unlock in productivity to do that.
It's probably even possible today with OpenClaw. That seems a bit risky.
Yeah, I'm not installing that on my work computer, that's for sure. So while we're waiting for this, I want to show you another thing that I've been working on.
Cool.
So, this is the EOS web monitor that I built. We'll reload it here, but this was 100% built with AI. So no real software engineer has helped. But we're rebuilding this for real now. But I was able to prototype everything that we wanted and all the different functions and things like that. So, I got everything working, and I went through a bunch of different iterations because it's like, we don't really know what we want. So what this does is it uses EOS's REST APIs. It pulls all of the data from the machines, puts it in a SQL database that it generates on the machine, and then projects that data to a web page that it built that we can get to through this IP. And you can see all of our machines are named after bears because Ursa Major, which is pretty funny. So right now, 3 of the machines are printing. One of them is ready for us to start our build on after the build's done. But you can see we also have a live video interface of the machines.
Wow.
So on the right, that's our M290 Flex. We're doing tensile bars. We're doing a lot of heat treat studies to look at lowering the cost of heat treat. So we're just running simple tensile bars, and we're doing different shared runs to try to lower the cost by increasing the flexibility of the heat treat, seeing what it does to grain structure, tensile properties, things like that. So as we have time in between parts, we fit those in. And on the left, we're printing some components. Can't really talk about that. And then the machine in the middle.
Baloo is resting.
Like I said.
Yeah.
But this is a live video feed of all of our machines right now. And this was all built, like I said, with AI. We also have, what's really cool is a email handler as well. So we have status reports on our machine. So every hour, it sends us a status report, what layers the machine's on, build platform temperature, chamber, pressure, everything, how many's printing, how many's idle. And what's really cool is when there's a build interrupt or where there's a stop, there's an issue, we get an alert. And so we can set up the filtering in the email to have a folder that gets our status emails, but then it goes, notification when there's an interrupt, when there's a machine issue, and then sends you a snapshot in real time of what the camera's looking at in the machine. So if we have a coder snag or short feed cause an issue or something, we see an image of what's actually going on in the machine.
You can act. Okay. Wow, that's really cool. That's really cool.
Yeah.
How long did it take you to build that?
It took me like a week. And like I said, I'm only doing this at like, 5%, 10% of my job.
Okay.
So like, and one thing I wanted to bring up, and part of the reason I want to show everyone just to show what's possible, but the real reason this was possible was because of EOS's really good API documentation. So this is kind of my call to the industry, and also, also to EOS as well. The real unlock in the future is going to be the companies that have really good documentation for how do these tools interface with the real world or with hardware, with machines. So great example is the Connect Core API that EOS has developed. There is really good documentation around that. So all I did was I took all the documentation, I fed it into Claude Code. I said, hey, here's all the documentation for this. What we want to do is build a, database that can query the machines every minute, every 30 seconds, whatever, and then pull the data off. Here's the information I'm interested in, powder in the dispenser, what layer the job's on, when it's going to be done, all that stuff. And then, build a database with that. And then once I did that, I said, okay, you have this database, now just go build a front end web page that anyone can view. And it can do all that, on its own without any prompting. But, so one of the things I really wanted to talk about is that, one of the key unlocks for like the next phase of, I would say, advanced manufacturing is any of these systems that we can create really good documentation that the AI can then use to ingest the data or to interact with the data.
No, you're totally right. I think system access, system openness to allow, I would still call you a power user today, right? You're definitely on the bleeding edge of additive, but really that means you're an early adopter, and that means the early majority is next, right? It's definitely key to scaling the technology, and for companies like yours to use additive to achieve a cost advantage, you're only able to do that by efficiency gains and by really pushing the limits of the technology. And this seems to be really the next frontier of pushing the limits of tech, which before that was, system reliability and new lasers, but that's all matured. It's going to continue to improve, but not at a rate as tools like AI are going to improve the tech, I think. And as you talk about advanced manufacturing, let me ask you this. So what does that mean for actually an advanced manufacturing cell in the next 2 to 5 years, right? Right now, we're mainly talking still connecting different tools within the additive ecosystem, but you could then also include post-machining. You can include inspection. You could include other aspects of the process chain. How automated do you think the full production chain is going to be, potentially even including robotics, with the help of AI, really?
So it's funny. I think robotics will kind of be one of the last things that gets deployed, but I'm gonna shelve that one here until the end. But I think this whole process is going to get extremely automated over the next year. I think that's going to be the name of the game. So let me just hit on a couple things that we're working on right now and that are almost ready and can be rapidly deployed. So good example is like build data reviews, right? There's some software out there that already can do that. There's companies that have built algorithms, but with these tools right now, you can just build them yourself. So I trained an ML model with Claude to detect short feeds, for example. And so now, eventually, when that becomes more robust, now we can just automatically review every build and flag any short feeds, and the operator can come in and check that. And then the further future state is it just checks everything it needs to and says, yep, it's good to go. And then you don't even have to look at it. So I think there's a bunch of different steps. So the first step is, how can we do more with less people? So a lot of that is AI flagging data that's anomalous, flagging defects that it finds during builds. And that enables you to add more machines without adding a lot of additional quality personnel or additive engineers, things like that. That's one key unlocker in additive, I think, is that we need to be able to add machines. We need to be able to scale cost effectively, which means you can't have engineers interacting with every single piece of this. It's got to be automated. So
Scaling CapEx without
yeah.
OpEx following the
Exactly. So we have automated data processing, automatic flagging things. I think, the automatic acceptance is, kind of what we talked about. I think it's going to take a long time to really have true validation of that. But like, it's already ready now to like build these workflows and build these pipelines. And the other thing that I think is super important, that not a lot of people understand, is that this data and the ability to view the data need to be integrated with your manufacturing enterprise system as well. So like, you need to be able to tie all of your components that are serialized and have qualifications and all of that back to all of the build data and all the information, and you have that feedback loop. So another key thing towards that automation is to have all of this data in a pipeline that's easily accessible. So I think that's going to be, when we talk about automation, like, it sounds weird to say that the operator is going to view the data, but the key is that it's easily accessible and it's easily all tied together, so that you don't have to spend a lot of time doing the task of, is like, okay, I got to click through folders, or it's on SharePoint, it's on a shared drive, or it's somewhere like, right, it's just in a database. And then you have a, front end that you can either build with Claude, or there's commercial tools as well, but then you can go in and all the data's there and it's interactable the way you want to interact with it. That's the huge unlocker. And then eventually those things will go to automatic validation, kind of like we talked about before.
Yeah, and therefore you're even not necessarily replacing humans. You're just, again, aiding humans, and these humans manage different, call them agents, that then the human still validates the final outputs and confirms it. Right? You're not taking the human out of in that regard.
Well, and it kind of goes back to our previous comment, where you're 2x or 3xing the productivity of the engineer. So now, instead of the engineer wasting their time finding connections between data, or what build was that in, what part serial number is that, instead of the engineer wasting this non-productive time, now it takes them 2 seconds to type in the serial number, automatically pulls up the build, pulls up the data, images. It already flags where there's a potential problem. And now the engineer spends, a minute going in, boom, oh, there was a short feed here. Oh, there's a recoder collision. Here you go. Put a discrepancy report on the part, and then move on to the next task.
Yeah, and therefore you also, I mean, if I really think about what you're saying too, but there's a big debate on, is the manufacturing sector growing in the US? Yes or no? Right? There's, I think, different voices if you listen to economists, or not even politicians, but there's not a lot of consensus on if manufacturing is today growing in the US. But if I listen to you, and if I listen to really, especially our industry, there is no doubt that advanced manufacturing is rapidly advancing in the US, and that is not due to tariffs. It is really due to, in this case, artificial intelligence making processes more efficient, allowing startups like Ursa to act like very large companies and producing similar output. But also, if you think about it, AI moved funding away from software companies or SaaS companies and applying it to hard tech companies, also like Ursa, right? And that seems to start to become a positive flywheel effect that I think is really going to help grow the advanced manufacturing sector in the US somewhat significantly over the next few years. It really kind of pops into my mind as I hear you talk, and as I hear you really shows the advancements that you guys have built really with a really small team comparably to other companies.
Yeah, absolutely. So we can check back in here on our slice. And so we'll go back to desktop. So this is the build that we just sliced. So it's pins, and then we have sample 1 and sample 2.
Yeah.
And then this is just a view. It's a hatch view of the parts. And so what I'm going to do is walk through the timestamp of the part. So it's going to print. So this is the normal hatch tile filling. So it's going from left to right because the gas flow on this machine is from right to left. So you can see it's filling each tile like that. And then now on the second part, we asked it to fill from the outside of the part in. So now it's going from the outside into the center of the part, which there it go. It did work.
Interesting.
So, again, not sure if it's super useful on this part, but really cool to see this completely automated workflow, where we prompted Claude, we took a generic file, and we were able to now slice a build and load it on the machine. So right now the build's on the machine. I'm going to go start it here, and I'm just going to print that same layer we just looked at, and we'll have to get this started, and we'll watch it with our video to see the same hatch pattern that we just created with Claude actually printing on a machine, all in the span of about 20 minutes here.
This is the coolest demo we've ever done on this podcast.
Well, yeah, hopefully everything still works. But I think this is really cool to show our workflow as well, because we haven't shown it in this much detail yet. But we can basically go and all I did was, in our slicing software, I set up our working directory. I put the CAD geometry in there, and then I clicked run on the slicer, and then it sliced the build, loaded it on the machine, and then all I have to do is hop in here and hit go. So it's a little, so it's a little shiny. So hopefully we'll be able to see it go here, but we should be able to see that pattern that we just looked at. In a second here.
Yeah. While we wait for the system to start. So today I'm speaking at an event called Project Manufacturing, which is a bunch of high school students that are building, that are working on a project with additive manufacturing. In that case, with FDM printers. What's your advice to a student that's is interested in manufacturing, probably is nervous about the future, doesn't really know, should it go into manufacturing, software engineering, into a trade? What's your advice to folks like that?
Man, that's a really good question. So it's printing right here, right now. Here's the first part, and it's going to print the second part right here. So sorry for the view. It's a little shiny on the first layer. So I think manufacturing is a super exciting field to be in, because, one of the things I hinted at before was there's a lot of challenge around the digital world interacting with the real world. So I think there's a really good option both on the technician and skilled,
Right.
blue collar work.
Yeah.
Trades work, exactly. So I think there's a really good option on the skilled trades work, as well as on the manufacturing engineering side, that enables manufacturing to just scale in a completely unthinkable way over the next few years. So, I would recommend that people find something that they're passionate about building in the manufacturing space. And it doesn't matter if it's a trade or if it's on the engineering side, as long as, you're looking at these new technologies and you're incorporating them and seeing how things are changing. I think there's going to be a lot of opportunity on both sides. And I think I'm kind of an optimist when it comes to AI, and that I think it's going to enable a lot more scale. And it just like all, you look at all the new technologies. There's always been a lot of negative press around any revolutionary technology, but every time we've had one, it's only grown everything so large that there's still opportunities for amazing careers and a huge wide range of things. So I think that manufacturing is, to me, the most exciting field to be in right now, and I think it's going to be even more exciting over the next few years as things continue to accelerate.
Yeah, I totally agree. And it's actually there is, if you think about the role of AI, it will also it'll make junior engineers senior engineers way faster, right? Because you don't have to go through, you still of course have to go through a learning curve, but you can accelerate that very significantly. You do have a buddy on your sides that can guide you in a way. Whereas if you start as a manufacturing engineer, for example, right, you're gonna have to learn everything the hard way, at least the last decade. And I think that's gonna enable a lot of new engineers to get into a seasoned mode way faster, and that's where the fun really starts, right? Where you can do work like you're doing, Tom, where you can also spend some time on development and really trying to push the limits of a certain manufacturing technology. And I think that's where it becomes very, very rewarding really quick.
Yeah, for me personally, as a director running the site, there's a lot of high level tasks that I have to do. So if I didn't have this tool, I might not get to do a lot of this development that I'm doing because I have a lot of other things that consume my time. So this tool has kind of given me the ability to do some of this fun dev work or this exploration work that I probably wouldn't have had time to do, or certainly not at the scale or the extent that I'm doing it now. And so it's just really an unlocker at almost every level of, automating tasks that we don't want to do, or giving you the ability to do a lot of this data interoperability between different mediums, between Excel and code and Word and even like academic papers. Like you can mix all these mediums really easily now, and that allows you to spend like a lot of time like doing the core engineering, the real fun work, I'll call it.
Yeah, it takes away the annoying part and gives you back
exactly
the fun of engineering. Well, Tom, this was, like I said, such an awesome conversation, such an awesome demo. I know you put some work into that as well, because of course, if Ursa prints something, it's usually not something you can easily show. So I do appreciate you really giving us a peek into the development work at Ursa, how you guys are pushing AI, you're pushing additive manufacturing, you're pushing your engine programs really as a leader in that space. And through your openness and your willingness to share your experiences, I really do believe that you're doing the industry a great favor, and you're helping the whole industry to advance and get to the next stage. So thank you very much for talking to me today.
Yeah, and thank you so much for having me on. And we're really excited about the partnership that we have with EOS, and we really appreciate the support. A lot of this is enabled because of EOS's openness and willingness to accept new technology. We were the first company to work with yourselves to enable this new workflow. And your whole team has been nothing but supportive of us. So we really appreciate the collaboration, and it's really kind of given me the last year a new vigor in additive manufacturing to kind of build what hopefully is the next generation of additive, which is deploying these really advanced new software tools to enable the next level of scale in additive.
Yeah. No, partnership makes this industry grow, and I think between our companies, but also a lot of other partnerships out there are really making that visible. So excited to see what comes out of Ursa next. I'm sure we'll have you back in hopefully less than 12 months, because there's going to be a lot on the news. So I'm excited to see what else comes out of your guys' organization. And also thank you to our listeners. Thanks for tuning in. If you like this episode, share it with a friend who needs to deploy AI in a way that Tom is doing it. A lot of efficiency gains out there to leverage on. So get on it. This was the Additive Snack podcast. I'm your host, Fabian Alefeld, and I will see you next time.